Hi, my name is Joe Keel, and I'm a master's candidate at the University of Wisconsin-Madison in the Environmental Observation Informatics graduate master's program. Basically, for my final project, I have been tasked with creating a climate change vulnerability assessment with help from the Wisconsin Department of Natural Resources. And basically, this climate change vulnerability assessment, or CCVA, is going to monitor plant species found both in Wisconsin and on a continental U.S. scale. I'm going to be adding to a NatureServe database, which you could see right here. In this case, it's just an Excel sheet. But it's going to rank the vulnerability of plant species to climate change, all the species that we end up inputting into um, this file. So basically, to arrive at a ranking, CCVA, or in this case, it's CCVI. There are so many factors that you could take into consideration to rank a species vulnerability. It can range from a species' natural history, its distribution, occurrence, habitat preferences, native versus invasive findings, and then maybe even its endangered status. However, for this case scenario, um, my Wisconsin DNR supervisor and I have found that we're only going to really measure temperature and then moisture. So basically what we're doing is the entire list of species, which is over 2,000 records of all these species. We have written all this code to basically have each and every species be accounted for and to fit within these parameters. So maybe some species are only really going to be found here where the temperature is greater than 6 degrees Fahrenheit, or maybe within this range right here of moisture. And we're just basically going to be trying to test and find where species are today impacted, how they're impacted today, and then um, projecting in the future and how they could also be impacted then. And so basically the whole point of this project, again, this is the final deliverable, is this Excel file from the NatureServe. Um, but the real meat of this project was kind of figuring out how to get the numbers into these two metrics. And so I'm going to show you the code, how to do that right now in ARC catalog. Okay, so now that we understand which metrics we need to fill out with that NatureServe Excel table, as in temperature and moisture, we now have to kind of play around with the data and manipulate it before we can really get into the code. And so I'm going to show you guys first is just data I received from a NatureServe employee. Again, we need temperature and moisture for um, for these metrics right here, right? And so what I was given were these image data sets right here. However, the only thing we're going to focus on is historical temperature var-F, temperature future F, and moisture annual. This is the data that we chose, as in when I say we, I mean my supervisor and I chose to implement just because that is, again, what is in that calculator within the Excel table. We don't really need precipitation, of course, or just this random image file from um, Central and South America. And so what we're going to do here is the first thing I'm going to show you is just something to kind of get around with this data that we kind of had to get around and figure out. Just because this data as is not really too accessible for the code. It can't really be integrated because it has this pixel type that is floating point. Um, Basically, because it is not an integer, it's a raster, but because it's not an integer, it just cannot really be utilized within the code. And so a way to combat this uh, is to take these three desired data sets, and by using the raster calculator tool, we'll multiply them by 10,000. I'm not going to share it right now because it's pretty self-explanatory, but after we use the raster calculator and multiply these data sets by 10,000, um, we can preserve the decimal values that would otherwise be lost by doing a raw float to integer conversion. And then on top of that, of course, we do convert it into an integer. And so I'm going to show you what that looks like right now. Again, um, these data sets are all going to be in this floating point. However, when I did convert them, I just put them right here in this data converted geodatabase. You can see temperature future, for example, that they now have this signed integer pixel type, which is awesome. That means they can now be, of course, used within the code. Again, we're only going to be taking into consideration and utilizing historical temperature, var_f, temperature future f, and moisture annual. We chose, of course, F because we're in the United States and Fahrenheit is what we use here. I guess the other difference you can tell is just the raster image goes from yellow to blue. So we're done with this. We're really kind of done with this now. I guess before I really show you the code, I'm just going to dive into, again, just kind of how I organize the data so it can make a little bit more sense, hopefully, to you guys. And this is about to be a lot of information, as you can see, but I'm only going to show you what I thought was pretty critical and what I think is pretty critical to explain. So the initial just entire species data set that I was provided that I'm running all of this code on contains, as you can see here, 1.1 million records. Obviously, that's a lot of data, and I found that when I tried to run the 4 different code sets, and I'll get into that in a little bit, on this data was just way too big for processing purposes. Each code failed, and because of that, I decided to split this data up into 6 different groups based off of families. You could choose whatever metric you want in terms of separating the data, but I just chose families, and I chose 6 of them because I had 6 computers at my dispense. I was able to run all of this code and process all of this code within the University of Wisconsin computer labs, and so I was lucky in that I was able to do this. But yeah, as you can see, instead of having 1.1 million species in the input data set, I made it so we had 242,000 in set 1 and 143,000 in set 3 and 56,000 in set 6, right? And so basically, what I did is my end game was basically to have 4 different code chunks, or 4 different models of code. One that represents moisture annual stats on a national scale, one that represents moisture annual stats on a Wisconsin scale, temperature stats on a national scale, and temperature stats on a Wisconsin scale. Why it's important to have both the national and Wisconsin scale is just to kind of compare and contrast your results and your species and what you're seeing. Maybe a species in Wisconsin is, doing really, really, really well and has a lot of high numbers and we know is not invasive, and maybe it's doing a lot better than in a lot of other states. And so just by having comparing data that can be compared, we can kind of just better understand the data in itself a lot better. So from this, again, I just want to highlight that there are 4 different code chunks, and in this model builder, they're all right here. But what I really just want to emphasize again, I guess, before I dive into it, is for this to work, if you're going to run this yourself, I do not recommend doing this on one computer. I recommend splitting it up. And so, again, what I did is I ran, I opened up each code. So I'm going to open up one right now. We'll do national temperature works. And I opened up this code on 6 different computers. And the only thing I changed was the first input, right? This is the second of 6. I had those 6 families. And so one computer would have the first, second, third, fourth, fifth, and sixth. And from there, I ran them all at the exact same time to get my national temperature stats all done at the same time. And so if that makes sense, I would run one code chunk on 6 different computers for the 6 different inputs simultaneously, then I'd move on to the next, and then the next, and then the next. And then eventually, once I got all of them, I got these 6 different outputs within each one. I was able to merge them together using the merge tool. and then input them into the final deliverable. That is the NatureServe Excel spreadsheet. Um, and so, yeah, and so now that I've explained all of that and kind of how I got all that together, I know that if you're here right now, you're going to have all this stuff at your expense, and you're going to have all these resources, and you'll be able to amend it and look through this yourself. But I'm just going to walk through a few things within the code, not the entire thing, not only because it's really, really big, but I just don't think a lot of it is too necessary to go over, but there are some key components that we need to consider. And so if I open back up this national T, I just named it, actually my supervisor named it iterate rasters national. The T stands for temperature, and then works, because this one worked and it took a few tries to get this ball rolling. So this is one code in itself. Again, it looks like a lot, and I'm not going to lie, it is a lot. But at the same time, if you just run through it for about an hour, you'll have a pretty great understanding of what everything consists of and what all the tools represent, all the inputs and outputs, and it'll make a lot more sense to you by just running through it. So I'm not going to go through every single component of this. What I will go through are what I kind of find to be the most important to take into consideration. And of course, again, you'll have all this at your disposal if you desire. If you're here, I'm sure you do have it all accessible. So first things first, again, the first thing I brought in was just the input that we're using. Again, I split them up into 6 different inputs just to help out with computers and their processing. From there, all of the species that are within that one input, we're going to iterate using just an iterate tool. In this case, we use iterate field values. I just want to highlight quickly that iterators are a special tool that help you repeat the task that's given the inputs. So basically, it's basically Arc just running this automated response on each input. So yeah, you're not running kind of one at a time, basically, right? From there, we also put that input into this feature class to feature class tool, and we want to name it this percent value percent, which is just kind of like the code or the format here in Arc that kind of just like names the species correctly. So scientific name underscore basically equals this percent value percent, and we'll name them all the species for you in a correct format. Side note, nothing to worry about. But on this computer, I have not run this model yet. As I've said, I will not run this model. As I've said, I ran these at the computer labs at the university. And so that is the only reason why there are errors here. Nothing to be too concerned about. From here, I think one thing I want to highlight is, again, this is the national. This is a national model, and we also ran, temperature on a state model. And so what I will do actually is I'll bring up the soil or the moisture on the state, just because different metric, different parameters, and you can just see how that looks really quickly and how it does differ just a little bit here in the initial stages of the code here in Model Builder. The big difference you're going to see is, again, we have the iterate, same input, feature class to feature class, but on that feature class's output, I'm going to run this clip tool. And that clip specifically is for Wisconsin boundary, because we only want to get the species that are represented within this Wisconsin buffer, right? Which we download from the DNR site, and again, you will have access to. And then we clip it basically to the same output, and then we run our metrics. And so just basically the big difference here, just make sure that you're running the correct boundary or have the correct parameters depending on the code that you're running. And so here we go. Okay, so now we're back here on the national temperature model, and again, right, we just created these integers that can now be utilized within the code. We're going to extract values to points, we're going to add field, we're going to calculate fields in both. These are both the exact same, and they're going to be the same for moisture too, just the different input up here. But the big thing to note is when we get to calculate field here, our expression or our query here is going to be the raster value divided by 10,000. So again, to even calculate these integers, we had to multiply that initial image data set we were given by 10,000, those raster values by 10,000. And so now we want to get those initial numbers back. And to do that, we're going to just divide them by 10,000. So that's what this indicates right here. And then we just want this expression to be in VB format. So that's basically how we're just going to be extracting this raster data to specific points. From there, once we get those outputs, and for the temperature, we just want these to kind of be like in correspondence with one another. And so that's why we're running temperature at the same time, and moisture is not included. Moisture is going to be its own thing, and again, follow very, very similar steps. Just be a little different in the input. From here, running feature class to feature class, big key takeaway here is that we just don't want, again, whatever the metric that's being tested to not be null. So that's the biggest takeaway from here. Again, you're going to have all this at your disposal if you're watching this video right now, I have no doubt. The next biggest takeaway after we kind of create our brackets is all of the code right here. Basically, this code right here, whether it's feature class to feature class, summary stats, add field, calculate field, delete field, this is just generating the columns in the final table that we want. And we're joining the field, of course, and then out here, we're getting outputs. And so this is still just adding field, just creating columns and filling in those columns with the data that we're processing via this code. So I'm going to walk through this really quickly, and it shouldn't be too much. Again, maybe you can have this opened up right next to you as I'm going through this as well. But this is probably the most important part of the entire code. Again, just to show you that Excel sheet, the metrics we're looking at is temperature and moisture. And NatureServe already supplied us with these ranges that they want these species to fall into, basically, depending on that metric. And so you have to be very careful to make sure that every species is accounted for. And to do that, you make sure that all these numbers, all these ranges are represented. And so here, what you can see is in the feature class to feature class, we're going to have greater than 6.0. Temperature future is going to be greater than 6.0. Our very first metric here is greater than 6.0. Then the same thing for, we'll go with one of the more, we'll go with the middle metric here. Let's go with the fourth feature class to feature class. So future temperature of RF is going to be less than 5, and we need to include that and future temperature of RF is going to be greater than or equal to 4.5. And that's going to match this guy right here. Even though it doesn't say, greater than or equal to 4.5, you just need to, just find what is representative and what's going to fit within each range here. And then the same can be said for the moisture, which is a little bit more challenging for me personally because these numbers are all negative. And so you kind of have to, of course, think about it a little bit backwards, but I'll show you what that looks like right here. So as you can see, here we go. So we're going to have Hammond moisture metric is less than negative 0.051, and Hammond moisture metric is greater than or equal to negative 0.0074. So 0.0051, and then it says 0.0073 here, but I had to adjust it to 0.0074 so it does still fit within the range. I know that doesn't look like it would be correct, but I promise you it is, and I can explain why that's correct once I show you why all species and how all species are accounted for. But again, this is probably the most important part of the entire code because we're trying to fit all of the outputs within these parameters here, these ranges here. And so once we do all that and we get all that, another huge step is just running summary statistics, and this looks the same for both temperature and moisture and national scale in Wisconsin. You're just going to include the field you want. You want the statistic type to be count, and you want to include the species name. So right here we're on moisture for Wisconsin. and it's going to look the exact same for temperature on a national scale, except for this future temperature varf, but count and species name is still going to be there. And then from there, from this point, you're just going to add fields. In this case, we're doing temperature bracket 1 greater than 6. And then here we're doing, temperature bracket 2, 5.6 to 6.0. You can't really do a period actually in ARC. It's just not very compatible. So we did a D to represent decimal. So that's what that lingo kind of represents. And then you run all of that, and from there you're going to calculate the field. And then you're going to end up deleting fields and joining fields. And again, you can look at all of those. I just feel like that's not all too important to discuss right now. As you're going through this, you'll kind of discover for yourself what everything is actually representative of. But the big takeaways from this is we're just right here creating the tables, and we're adding and deleting and calculating everything we need to, so we're able to just get the correct outputs that we need. And so then finally at the end, after we calculate everything and input everything we need into the correct columns that are being generated, we're going to run a table-to-table tool. And again, we're going to do that percent value percent. So the species name is like actually considered here correctly and should be considered here correctly. And then from that, what we're going to do is we're going to run the append tool, which puts everything together and works everything in the correct way that we want it to work. And then we're going to run a delete identical tool, which is going to represent the species name, all the temperature brackets, and everything we need. However, the big thing that we want is, and the only thing we really want to consider is the species name in itself, because we just don't need that. It's already in the final table. It's going to be outputted, and so therefore we just don't need the species tool or the species name to be in the final output table. So right there is kind of a quick generalization of this entire tool and of the tools, of the modules, of the code and everything that was used here in Model Builder for each data type, for each metric. And from this point, I'm just going to show you the output, and then we'll take it from there, and we'll basically be done here. But basically what this is going to look like is, again, after you run all 4 metrics, they're all going to show up in the geodatabase because that's what I set them to. And then we just looked at, temperature national. And so this is what your end product will look like. This is only the second family because I inputted the second family at the very beginning. And so I don't have, a ton of species, but I do have a ton of records because, as you can see, this one species occurs 257 times. This species occurs 197 times, and so it's just a lot of data to take into consideration. However, a really, really important part, if you're writing this yourself and you decide to, run this kind of on your own accord, you just want to be sure that all these numbers add up. And so here we go. So this species, there is a sum of 42 records. And so I need to make sure that 18 plus 17 plus 7 equals 242, and in this case it does. And if you know that the numbers all add up, then every species is accounted for, and that all those brackets that you filled in with all those ranges within both metrics, temperature, and moisture, you know that everything's accounted for and you're good to go. On top of that, you know that, again, these were all of the columns created within that like big chunk of code, and you know that whatever is in temp bracket 3, temp bracket 4, temp bracket 5 is also going to be the percents that are given within each bracket as well. And the percents, of course, will also add up to 100. And hopefully they do. And if they do, that means you did the entire model correctly. And then from here, that's just basically a way to check yourself and make sure everything is accounted for, everything is correct. Um, and again, here's a smaller one, so we'll do it now. I have a sum of 20, and all I have is this species was only found within this temperature range, and therefore 100% is in the percentage brackets, which we again created in that model as well. So from here, again, this is only one of 6 outputs for this one temperature stats national metric. And so after I generated all of them, what I did is I used the merge tool to combine each one together. And then I was able to export that into Excel, into the NatureServe final database. And I was able to generate both a national stats database and a Wisconsin stats database. I just did it in terms of tabs just to keep it clean and have only one file type. But as you can see, I have every species generated right here in this database, and I'm sure you'll have access to this as well. And from here, of course, I also have all of those numbers that we need for both temperature and moisture for each species. One final thing to note is that the numbers that are generated are going to look a lot different for Wisconsin than they will nationally, and that's because there's a lot less range in Wisconsin than there is on a national scale. So what I found is that on the national scale, every column was accounted for at times, except for having a temperature greater than 6 degrees Fahrenheit. However, on the Wisconsin stats, things look a lot different, right? Temperature is only really between this 5.1 and 5.49 Fahrenheit. And that's okay, that's to be expected. Again, Wisconsin is a much smaller scale than including the other 49 states. However, yep, the soil was found to be a little bit more similar to the national moisture because it's represented in 3 different metric types right here. And so, yeah, so that's kind of this is kind of the end deliverable right here is all of this information and these stats. And yeah, I really wish you guys the best with whatever you're doing with this model and data set and deliverable. And I think I just want to lastly say that this CCVA project will help to answer some questions about climate change and species responses, both on a national Wisconsin scale, because we computed both of those. However, it should also serve as a first cut to see where there are patterns in the landscape, maybe by climate change or general species distribution patterns, and help to place the scores calculated into context. This project and data set will continually be improved upon and interpreted for years to come as we continue to struggle with climate change and seek to further understand its many impacts on plants' performances. And so again, this is just really a first cut. And again, if you're here, you're free to manipulate and amend everything you've seen. And I wish you the best of luck in what your project is and what you're doing. Thanks.